Good morning, everybody. This is Shane Hale here from Rosemount Gas Chromatographs. Thank you for joining us today on this Validating Gas Chromatographs webcast. As you can see, we've just started a poll at the beginning of the webcast just to see where everyone is at the moment and see what people currently do. I'm looking at the poll questions coming in now and seeing the results are, and we'll talk about them in a couple of slides. So what I'll do is while we're waiting, there's always a few people that take a little bit longer to log in and get into the webcast. So while we're waiting, we will have this poll up. And I'd just like you to tell us what you're doing currently for validating your gas chromatograph. Analyzing the cal gas as an unknown, maybe a random sample or a known concentration around robin, comparing to the ultrasonic flow meter, speed of sound, an inspection suite, or just looking over the GC and seeing that it's still there. So while we're waiting, we'll start in about 40 seconds now, but while we're waiting for everyone to get on, we'll just hold this poll up there and see what everyone is currently doing. Just quickly as well, this webcast will be recorded and will be available later. For those that are on the recorded version in the future, you will also be able to take this poll as well, and we'll, when you take the poll, we'll get the results over email. And also, if you have any questions, we'll get them later and be able to email you responses as well. So even if you are not on the live event, don't worry, we'll still respond to your questions. So it's 10:02 now here in Houston, so we'll start the main part of the presentation. Before we get into the meat of the presentation, what I will do is first of all give you some basics on the environment, the webinar environment that you have here. The main screen obviously is where you can see the slides and video and the polling questions that you just had just there. If you have any questions, we are connected audio over the internet, and so to ask any questions, just enter them into the question and answer box down on the bottom of the main screen there, and I will respond to them as we either get the questions or at the end of the presentation, depending on the question. Just in case you don't know who I am, my speaker bio is up on the top right-hand corner there. Resources link is on the below it there. We don't have any resources for this particular webcast, but if we do have any links or any material, we'll put them there in that section. Media player is down on the bottom right-hand corner there. That's where you can control your sound. If you want to tell everybody out there in the Twitterverse that you're watching an awesome webinar, you can share it using the buttons on the bottom-hand corner. And if you want to contact someone, if you want a salesperson or a technical question, you can click that button and it'll open up your email client so that you can contact us. So that's the basics of the environment. Now let's get into the main meat of the presentation here. We're talking about validating gas chromatographs today. So what we're going to do, we can try and keep it inside the hour. And first of all, we're going to quickly define what we mean by validating GC. So we're all starting on the same page. Then we'll talk about how to verify the previous operation of the GC, verify the current accuracy of the GC, and also then we'll talk about how to predict the future performance of the GC, and finally just a quick summary of the reporting requirements we typically have. This presentation is focused primarily on the gas custody transfer application, where validating the GC is a part of maintaining the custody metering system. But the principles apply to any GC and to some degree other analyzers in other applications as well. But we will be focusing on the custody transfer application, the typical C6 plus or C9 plus application. So looking at the poll results, it's always interesting to see what people are currently doing before we have this kind of training. And there's no surprise there that analyzing the calibration gas as an unknown is definitely the most common way that people validate their GCs. Running the cal gas, looking at what the analysis of the gas is, and then checking against the calibration certificate that comes with the bottle of gas. That's a very common way that people validate GCs. Another way that people validate GCs is the second most common, which surprises me actually, is running a known sample. Now that's taking a verified sample that is not the calibration gas and checking it against the GC, so analyzing it and checking the composition against the known composition of that gas. That is a very good test actually. It just can be pretty hard to manage. Comparing the calculated speed of sound to the measured speed of sound, we've got no one on that, which doesn't surprise me as far as validating. People often validate the ultrasonic meter using that, but not so much the GC. An inspection sheet that looks at the calibration report and other checks, and we'll talk about that in a little bit more detail as we move on. I do see a lot of companies that have a response factor check sheet. I'm surprised we didn't get more people with that on the webcast. And obviously there's that question, the answer at the end, look out the window and check that the GC is there, hey, yep, no one's stolen it, it's still doing okay. And there's always one or two people that just verify the GC by just looking at it. So that's interesting though, because the biggest response there we got was analyzing the cal gas as an unknown and comparing to the certificate. And I figured that would be one of the most common ways. And so first of all, what I want to talk about is what we're trying to do when we're validating the GC. So it's we're essentially certifying that the analyzer has been operating correctly and accurately, and also will continue to work accurately until the next validation period. Throughout this presentation, I'll often interchange the terms validating and verifying, but for our purposes today, they mean essentially the same thing. Note that validation is not calibration. During a calibration, the GC calibration factors are adjusted to measure correctly. Strictly speaking, a valid verification or validation is only confirming the measurement and operation of the GC is correct. Now, during a validation process, it may be found that the GC does need to be calibrated, but that's not the purpose of the validation. So you may find during the validation process that the GC is not accurate, so you will go ahead and calibrate it, but that's not the main purpose of the verification or the validation. The main purpose of the verification or validation is to confirm that the GC is analyzing correctly. So running a cal gas as an unknown, it was about 52% of the people in the audience says that's what they do for validating their GC. I hate to tell you this, guys, but that's not really a valid method of validating the GC. Now, let me show you why. Really what's happening when you're analyzing the cal gas is you're checking that the GC is doing what it's told. You're seeing that the GC has been told to read this when I put this gas on there, and guess what? The GC is doing that. And what I mean here is if I look at what happens during the typical day of a gas chromatograph, on a custody metering system, we often calibrate early in the morning. So we calibrate at, say, 6 or 7 o'clock in the morning. Then we get to site, we do our validation. About 1, 2 o'clock in the afternoon, we do a validation. And we run that calibration gas. But at 6 o'clock in the morning, we told the GC to run that cal gas and to change its results to read a certain values for that cal gas. And so whenever it sees that cal gas, it's going to read those values. It doesn't mean that the GC is running accurately. And a story that I often talk about when I talk about this is I worked at a refinery once where we had this brand new dead weight tester. And a lot of people know what a dead weight tester is. It's used for calibrating a pressure transmitter. So we get this new dead weight tester in, and the storeman looks at it and he says, wow, this is an expensive piece of equipment. I better make sure no one steals these weights. And so what the storeman does, we have these very precise calibrated weights that have a very precise mass so that we can use it to calibrate our pressure transmitters. The storeman goes along with his big engraver, his metal engraver, and engraves Port Standback Refinery over all of these calibrated weights. And so now they don't have the same weight that they used to be. So they're not accurate. But if I take that deadweight tester and I go and calibrate my pressure transmitter, and I tell that pressure transmitter that whenever it sees this weight, put on, it's going to read 1,000 kPa. We're metric in Australia, so it was 1,000 kPa. It's not correct, because it's got that big engravement on there that's actually changed the weight, so it's not correct. But I've calibrated it to read 1,000 kPa. I go put it on the process, it reads incorrectly. It's reading incorrectly, so I take that transmitter back, I put it onto the deadweight tester, and I check it with this bad calibration weight, and it reads 1,000 kPa. So even though it's telling me what I've told it to tell, it doesn't mean that it's correct. And that's the problem with running a cal gas as an unknown. It will always read what it was forced to read in the calibration run. It doesn't mean that it's running accurately, it just means that it's going to read what you've told it to read. If the GC is set up incorrectly, has an issue, or the calibration gas blend is bad, then this calibration can actually hide the issue and result in an accurate analysis for the sample stream. It'll tell you what the cal gas you've told it to read with the cal gas, but it doesn't mean it will analyze the stream gas correctly. And so running the cal gas as unknown is not a valid method of validating a gas chromatograph. It's important to understand that it's only telling you, yes, it's reading what you've told it to read. It doesn't mean it's accurate. And so what this whole presentation is all about is how to validate that your GC is running accurately. So looking at our schedule for validating a GC, often in metering systems we will regularly validate the gas chromatograph, validate the operation of the GC. And the important thing though is that this process of validating the GC is not just for today. What we really need to do is we need to check that it's running correctly today, but we also need to validate that it's been running since the last validation. And then we need to try and confirm and certify that it will run accurately until the next validation. And so running a validation of a GC shouldn't be just checking that it's working today. It should be checking that it has worked correctly, that it is working correctly today, and that it will work correctly into the future. So first of all, what we're going to do is we're going to check that it has checked the alarm and event logs to make sure that the unit is operated correctly. Then we're going to check the calibration of the operation. And after that, we're going to look at what we call the retention time drift to predict the operation into the future. So first of all, let's have a look at the checking the alarm and event logs to ensure that the unit has operated correctly and no changes have been made. So there's two great reports that's inside a GC. Now, obviously, we're going to be focusing on the Emerson gas chromatographs here, but any gas chromatograph out there, even those inferior ones from the competition, they will have alarm log and event logs as well. And it's really important to check that the check that the GC has operated correctly leading up to it. And the alarm log and the event log can show you that. So first of all, we'll look at the alarm log. Okay, so this is the Mon 2020 software. To look at the alarm log, we'll go to logs and reports, alarms, and alarm log. And we're going to look for some common alarms. Now, some of the common alarms that you can look for, obviously in our manuals and actually in the help files for the GC, we have a list of all of the alarms that you can possibly get and a brief description of what those alarms mean. But common alarms we might want to look for is like GC idle. GC idle means that the GC was left not running. So if someone has gone to site, they've stopped the GC from analyzing, and then they've left site and they've come back later on and turned it back on again. That's a problem because you're not reading, you're not analyzing the sample during that time. It's off, so your billing may be incorrect. Power failure, it's good to know if a power failure has occurred. Going down further down the list, there's things like RF deviation. Response factor deviation is telling us that, hey, there was an alarm that was raised during a calibration run, during a daily calibration cycle. The calibration failed. That indicates to us that there was a problem with this GC during the period leading up to this verification. Auto valve timing failure, that's something for the 370XA. That means that it's tried to adjust the valve timing and it's failed. It's telling us there is something wrong. So it's important to look at these alarms to see if something has gone wrong during the period. Also, I really want to highlight that when we're validating and verifying a GC, we're proving that this GC is working correctly, and often in the custody transfer world, this is done so that we can prove that our measurement was good. So it's really important that when we look at these alarm logs and event logs and everything else that we're going to look at today, that we save it. So what we can do on our software, we can select the range. So you want to select the range from the last validation period to the current period today. And we want to save it. We want to save it, and I typically will save it to a folder on that particular date. You can see there I've got a dated folder there. I want to save all my information to one folder to say this is all the information that we have saved at this verification, on this validation date, so that I've got a good record to prove that everything was working correctly and will be working correctly, and that I actually did something today. So we'll save it onto the computer. Now, that was the alarm log. So we looked at the alarm logs, made sure that there was no alarms, or that if there was alarms, we understand what they were and understand what that could do to our measurement. The next thing is we're going to look at the event log. Now, I have a special name for the event log. I love the event log. When I was out in the field working as a service technician, I used to call the event log the lie detector, because whenever you change anything on the GC, it goes into the event log. And I would get to site as an Emerson technician. I'd get to site and the local guy would say, oh, no, I never touched anything. I never changed anything. And then I would open up the event log. I would open up the lie detector, and I would see all of these changes inside the event log. Things like change the response time, retention time, change the maybe change the inhibit times, or change some of the integration settings, and then they wonder why it's not working. So I love the event log. It tells you if anything's been adjusted. Now, it's okay if some things have been adjusted. That's what technicians do in the field, is they will sometimes adjust the GC to get it working correctly. But it's important to know, if you're validating that the GC is working for the last period, since the last validation, it's important to know what has changed. And so we take a look at this event log, and like we did before, select the range from the last validation to the current validation. Then we save it. And we look for some common events. Two of the most common events that I see all the time that really raises some red flags for me is, one is the forced cal. A user has run a forced calibration, and basically what's happening here is that when we run a normal calibration, there's certain checks that the GC does to confirm that it is running correctly, that is calibrated correctly. It looks at the response factors and makes sure that the response factors haven't changed by too much. In a normal calibration, if the calibration response factors have changed by more than 10%, it tells the GC something is wrong, and so it will raise an alarm. A forced calibration is where it no longer checks to see that it was a good calibration. It just updates the values. It's forced to update. Now, there is a valid reason to use a forced cal. If you have fixed a problem, if you have changed some settings, then you will need to run a forced cal. But that means that you're running it because you know you've fixed the problem and you want to reset the calibration of the GC. But if I look at an event log and I see that there's nothing there except for a force cow all by itself, it tells me that someone's had an alarm and they just hit force cow and force it to read whatever they've told it to read. They haven't fixed the problem. It's the equivalent of lifting up the rug and sweeping the dust under the rug rather than actually cleaning the floor. So it's really important to look for things like this on the event log. A force cow is a big red flag that tells me that, hey, something happened to this GC. There may be a problem with the measurement. Another one to look for is a halt. That means someone has stopped the auto sequence, and so that's important because if you are using this GC for metering, if you're using it to give you energy values through a meter run, it's important to know when it has been running and if it has not been running so that those results would not be accurate. So that's how we check to see that the GC is running correctly before the validation. So now we're going to really get into the meat of it and look at how we check the calibration and operation of the GC today. And remember, running a cal gas as an unknown is not really a valid way of proving that the GC is working correctly. Another way is called the round robin testing. And that's where you're taking a known gas, so you take a known gas from your central lab or from a central location, you bring it to the GC, and you analyze that gas, and it needs to be significantly different than the calibration blend. There's no use if it's exactly the same as the cal gas blend because the GC has been forced to read that blend correctly. So using a round robin, a blind gas sample or a test blend, it needs to be different than the calibration blend so that you can see if there's any errors in the analysis that might be hidden by the calibration. The test blend needs to be known to a high degree of uncertainty. That means it needs to be a very accurate sample because if that test blend is only a 10% uncertainty blend, then the analysis results from the GC are only going to match that certificate within an uncertainty of 10%. So it's important to have a high degree of uncertainty for that test blend. And also that test blend must not be contaminated. It's got to be stored and handled carefully to maintain the composition. We've got to make sure it doesn't get too cold and then the gas taken out. We've got to make sure that it doesn't get poisoned by other samples. And so it's really important to maintain that test blend very carefully so that it doesn't get contaminated. So round robin tests, I do like round robin tests. I think they are a very valid test and they can really show up some issues on a major pipeline. Round robin tests are really good if you have lost and unaccounted for issues across a pipeline because you can take one gas sample and you can run it through all of the gas chromatographs along a pipeline and you can quickly see where the problem is because all the GCs that are working correctly will read the same and the one GC that's a problem will read differently. So a round robin test is a good, valid test. However, it can be very hard to manage and it can be expensive to manage as well. There is another way. The other way is checking the response factors. And what we're doing here is we're checking that the calibration of the GC essentially is following the laws of physics. We have these detectors we're going to talk about today, a thermal conductivity detector that responds in a very understood way to the component we're trying to measure. And so understanding how the detectors respond to those components can provide a very effective way to validate the operation of the GC. Changes in the response of the detector to the components can indicate changes in the analysis that cause inaccurate measurement. And so if you see suddenly that the response of the detector to one particular component has changed, but it hasn't changed for the other components, it really is telling you there's something wrong with that measurement. And so it's a really effective way of understanding what is going on with the GC and understanding if the GC is accurately analyzing the gas. So before we get into this in detail, let's have a quick look at a typical calibration report. Obviously, this is from an Emerson GC. I think this looks like a Model 500 to me. So what we have up the top is the usual stuff with the date and time. Then we have the cal gas concentration. This is a calibration report. That cal gas concentration is actually the values that have been entered from the certificate that comes with the bottle. So we have entered the values, and these are fixed values that go into the GC, and they are fixed every time we change a cal gas bottle. Then we have the original response factors, or the old response factors. These were the calibration response factors before we calibrated the GC. Then we have the new response factors. We have the deviation between the old and the new response factors, and we don't expect to see a large deviation. We do expect to see a slight deviation from day to day. Usually that's because of changes in atmospheric pressure and some other things, but we do expect to see a small amount of change, but not a lot. Then we have the retention times, the old retention times, a new retention time, and a deviation between the two retention times. And on the old Model 500 and the Emerson final calibration reports, you'll see that there's a little asterisk or star there that is next to all of the factors that have been updated. So the first thing you've got to do is we've got to make sure that the concentration is entered correctly into the certificate. And so what we do is we look at the certificate there on the left-hand side. You see a certificate on the cal gas bottle. We need to first of all confirm that the correct concentrations have been entered into the GC. You're not going to get very far if they aren't entered incorrectly, and so that's really the very first thing that you need to do. And now what we're going to do is we're going to look at what we call the response factors, and we're going to look to make sure that they respond, the GC is responding essentially according to the laws of physics. So let's get some basic detector theory going on here with the thermal conductivity detector. A thermal conductivity detector is measuring the thermal conductivity of the gas going over it. So we have pure helium going over the pure helium going over the detector, and helium has a very high thermal conductivity, and so lots of heat is removed from the detector, and so the temperature of the detector is reduced. When the temperature of the detector is reduced, the resistance of the detector increases, and that's our measurement. So the helium goes across, takes away a lot of heat, and then our component of interest goes across. In this case, it's going to be methane. And there's a mixture of methane and helium that goes over the detector, depending on the concentration. Methane has a much lower thermal conductivity than helium, so less heat is removed from the detector. So the temperature of the detector actually increases, so the resistance decreases, and that's the measurement that we see. That's the result that we see from the methane going over the detector is a decrease in resistance, and actually electronically we see it as a millivoltage increase. And so that's how a thermal conductivity works. It's responding to the changes in thermal conductivity going over the detector. So looking at how we calculate the response factors, for most C6 plus GCs, most commonly we will use what we call the area. So it's response factor equals peak area over the cal concentration. This is how we're calculating the calibration factor. Now there is an alternative. Sometimes in some applications we'll use peak height, where we'll use the height of the peak to calculate the response factor. That'll give us a much smaller response factor, and what we'll be focusing on today will really be on the peak area response factor, because that's what we commonly use for a C6 plus or a C9 plus gas chromatograph in the custody transfer world. But really both factors are used and the principles are the same. So let's have a look at thermal conductivity, because this really gives us a really good understanding of how the GC should respond to individual components. So we use helium as a carrier gas because it has a really high thermal conductivity, especially compared to methane. So there's a very large difference between the pure helium, and on the left-hand side you see a little picture there of the detector. Pure helium is going on the reference side, and on the other side we have the mixture of helium and whatever component is coming out, in this case methane, and there you see you have a very large difference in thermal conductivity, which is the response of the detector. That's what we're measuring. Let's have a look at the other components that we commonly measure. So we look at nitrogen, ethane, propane, isobutane, and normal butane. You can see that they all have different thermal conductivities. This is a basic physical properties of these components. Well, when you compare them to helium, they're different to methane. And you can see there that there's a much larger difference between the thermal conductivity of nitrogen and the thermal conductivity of helium than compared to methane. And so what we expect to see is that we'll see a much larger response to nitrogen from the detector compared to the response of methane. And also we'll see a much larger response for ethane, and a larger response for propane, a larger response for ibutane, normal butane, and so on through the hydrocarbon chains. And so using this knowledge, understanding that the detector responds to the thermal conductivity, really gives us a great tool to understand and to confirm or validate that the GC is running correctly. So when we look at our calibration certificate there, I've taken a little cutaway there of the calibration certificate. And what we're doing is we're looking at these response factors. So we want to look at the smallest response factor. So I look at these numbers down here, and I see that methane is 6.888 times 10 to the 6. Times 10 to the 6 means we move the 0 6 times over. Times 10 to the 7 is we move the 0 over 7 times. So times 6 is a much smaller number than the times 7 numbers here. So we have 6.888. That is the smallest response factor, which is good because it is the one that has the closest thermal conductivity to helium, and so it should have the smallest response. Then nitrogen, then CO2, then ethane, propane, ibutane, N-butane, neopentane, ipentane, normal pentane, and then C6+. And so by looking at these response factors, we can confirm if the GC is working according to the laws of physics. If one of these response factors is not in order, say that the ethane value is at 9.78 times 10 to the 6 and is lower than carbon dioxide, it doesn't mean that because it's a Thursday morning that ethane has a different thermal conductivity. It means that something is wrong. It's not responding according to the laws of physics. And so something is wrong. We now know that the ethane measurement will be inaccurate. And so that's why we're going to use these thermal conductivities to really understand if the GC is working correctly and to validate and confirm that the measurement is correct. Now, what we can do, and what a lot of people have done, is they plot these response factors, and they'll plot them on a chart, and you can see a very distinct response there. You can see methane is at the left-hand side, and the response factors go up from there. In the GPA, there's a GPA standard that actually says that you can plot the normal hydrocarbons, the methane, ethane, propane, normal butane, normal pentane. You should be able to plot them on a log response factor, log molecular weight chart and get a straight line. So this is a very known relationship. And so it's a very useful relationship to understand to validate your GC. Now, response factors will change over time because when we inject the sample into the GC, we inject the sample at atmospheric pressure. And so as a result, you will see some changes in the response factors due to atmospheric pressure. The higher the atmospheric pressure, the more of the sample is injected, and so you'll see a higher response factor. The lower the atmospheric pressure, the less sample is injected, and so the lower the response factors. We expect to see small changes in the response factors, but all of the response factors should change. And so when all of the response factors change, it's okay. That's a normal reaction. We expect that to happen. But the response factors for individual components shouldn't change relative to each other because the thermal conductivity of the components won't change. And as the response factors are dependent on the relative thermal conductivity to the reference component, then we should see all of the response factors move in the same way. And so what we can do is when we plot the response factors, we can look at here, you look at this plot that I have here, we've got in the table in the bottom, you've got all the components. We have the response factors. I also have the log response factor because that's how we plot it in this case here. And what I've done is we've calculated a ratio of the response factors to, in this case, methane. So methane's the relative, is the reference component, and so that has a response factor ratio of 1. Then nitrogen, the response factor is 1.27 times over the methane response factor. And the carbon dioxide response factor is 1.52 times the methane response factor. And so what we've done here is we've plotted the response factor ratio. During some testing in the factory here, we have calculated some ideal response factors. And so here you see the ideal response factors, and then there's a deviation in the response factors here. And you can see we should probably add a few more decimals to these numbers because they look like they match, but when we look at the complete number, there is actually some deviation there. We do expect some deviation because there's an uncertainty in the calibration gas mixture. There's an uncertainty in the actual detection, and so we do expect to see some deviation, but we expect it to be within a certain tolerance, and generally that tolerance is 2% for very large components like methane and ethane and nitrogen and CO2, and about 5% for the other components. And for the C6 plus, we tend to see about a 10% deviation in the ideal response factor, simply because it's a very, very small component, typically 0.03%, and so it's way down there in the detection limit of the detector. So this is a good response factor graph. So let's have a look at some issues that we've seen in the field before. Hopefully. This one here, this is a great example. Carbon dioxide. We can see, looking at this graph straight away, we can see that there's a problem with carbon dioxide. And this is one that I saw a few years ago. This is where the CO2 cow gas concentration was entered incorrectly. Someone had changed the calibration gas bottle, but they hadn't updated the calibration concentrations inside the GC. And so when it was calibrating, it was told, hey, there's 1% CO2 in there. When really, in that cow gas, there was 2% CO2 in there. And so it read incorrectly. Now, if I analyze that cow gas as an unknown, I probably would have found that as a problem, because I would look at the certificate and see, well, actually, no, that's not true. I would look at the certificate and I would see that it is reading what it should be reading, but it would be wrong. And so that's an issue here, is that the carbon dioxide was not entered correctly into the GC. Another problem that we have here is, in this case here, you can see that the normal pentane response factor is very low, and the C6 plus response factor is high. What's happened here, we have what we call a backflush operation, and that backflush was a little too early. So it was taking some of that normal pentane and actually putting it into the C6 plus. And that was a valve timing issue. If you were calibrating a gas as an unknown, if you were analyzing the cal gas as an unknown, you would never see this problem. Because you would look at the analysis and compare it to the certificate, you force the GC to read those values when you've read that gas, but you're reading that gas incorrectly. It'll still give you those values, but it won't be a correct measurement. Looking at the response factors will tell you that there is an issue. And in this case, a normal pentane was being backflushed into the C6+. Another valve timing issue here, we have what we call a dual column arrangement inside the GC. In this case here, the ethane value is reading too low. The response factor for the ethane is too low. That's telling us that the valve timing for the ethane propane split, the dual column valve timing, is cutting into the ethane. Analyzing the calibration gas as an unknown will not show you this. It's only by looking at the response factors that you will see that this is an issue. Another one that we see commonly is the nitrogen value is too high. The nitrogen value response factor is too high, and that really is telling us there's a leak in the cal gas lines. Basically what's happening is some air. Air is 78% nitrogen, 21% oxygen. There's some nitrogen leaching into the cal gas through a leak in the lines or around the regulator, and that's causing an incorrect calibration, or actually the most common issue here is that we are someone has calibrated or changed the calibration gas bottle and they haven't allowed the cal gas to purge long enough, and thus there's still some air in the lines from when they changed the cal gas bottle. So by looking at the response factors, you can see, we've looked at 4 different problems there. We had a CO2 calibration concentration was entered wrong. We had a valve timing issue for the backflush. We had a valve timing issue for the dual column. Here we've got a leak in the cal gas lines or not enough purging in the cal gas lines. We've found these problems by looking at the response factors, and none of these problems would have been found if we'd analyzed the cal gas as an unknown. And so that's why it's really important to look at these response factors as validating your GC to confirming the calibration is correct and the analysis is correct. Excuse me. So when we're looking at relative response factor ratios, we calculate that by the response factor of the component over the response factor of methane. In this case here, and this is what we have inside the 370XA. What we've done is a lot of people with our Model 500 GCs and our 700XA GCs, they've done this manually. Maybe they have a spreadsheet that calculates these response factors and the ideal response factors. Well, what we've done with the 370XA, really trying to emphasize the ease of use and making it easy to keep these GCs running accurately, we've built this into the 370XA. And so here you can see the list of relative response factors that we have inside the 370XA, all relative to methane. Technically speaking, we actually compare some of the other components to normal butane because of the flow during a dual column action, but that's a bit of a technicality that we don't need to go into today. But what we're doing here is we're confirming that all of the response factors, we have all the response factors have the same ratio to methane that they should have according to their thermal conductivity factors. And when we do it inside the 370XA, not only does it happen on a validation run, it happens every single calibration check. Every time it does a calibration, it will check that the response factors are in order and that they're within limits of the ideal response factors. So that we're really trying to, with the 370XA, we're really trying to make it easy to keep this GC running as accurately as possible. Now, I will say that because we're doing this inside a GC now, we will get more alarms. We will get more alarms because now you're getting a much earlier notice that something is wrong. But when you're using these GCs to measure energy that's going to be used for billing and goes into loss and unaccounted for calculations on a pipeline, then you really want to know as soon as possible that something is wrong with the analysis. And that's what we're doing here, is giving you a really early notice that something is going on with this GC and that you need to check it. So that I would much rather get an alarm telling me that my GC is running inaccurately than having my director or VP of operations come down and say, why do we have really high loss and unaccounted for on the on the pipeline at the moment. So we're really trying to make it so you can run as accurately as you possibly can and get an early notice that something is going on. So that's how we verify that the GC is running accurately. Now, just before I move on to the next section, I do have a few questions that I'd like to get to. One comment was about round robin. Round robins are known as a check gas in Europe. That's true. That's often they'll actually have them installed permanently as a check gas. So you'll have a calibration gas and then a check gas or a verification or validation gas. It's the same thing as a round robin. The difference with a round robin is that you're taking that bottle from one site to another, whereas a check gas is often installed at the location permanently. What's the expected range of deviation for response factor deviations? We're talking about here, we're talking about on the calibration report. I'm just going to bring up the calibration report again. I can't find it now. The expected response factor deviation range, well, it needs to be under 10%. But typically we'll see the deviation from day to day will be less than 2%. And most often it's below 1%, but if you get a cold front come through or some kind of weather pattern come through where the atmospheric pressure changes drastically, then you may get up to 2% deviation. We actually set the alarm at 10% on the old Model 500s, 700XAs and the 370, but we also have some customers that change the response factor deviation down to 5%. Now, the question is, where does the ideal response factor ratio and the ideal deviation show up? It shows up inside MON 2020 on the reports, on the calibration reports, and also in the component data table is where you see the ideal response factors. And there's a question about, can you get these response factor graphs in a simple menu in the software? Actually, there is a response factor graph that is in the software in the MON 2020. It's available on all of our XA series GCs, although it only shows the normal hydrocarbons because it's really according to the GPA standard. So there's a GPA response factor chart that is in our MON 2020 software. I didn't show it in this presentation, but it is available in the MON 2020 software. So that's answering the questions that I have so far. So now I'll move on to the next section, which is now that we have proven the GC was okay leading up to the verification. We looked at the event logs, we looked at the alarm logs. Then we now have validated the GC is calibrated correctly. We've looked at the response factors and validated that the response factors are in the correct order and with the ideal response factor ratios, and so we know the GC is now running accurately. The next thing to do is to predict what the operation is going to be like until the next validation. So what we're going to do is we're going to have a look to see what could happen over the next period, over the next month or 3 months, depending on the validation period. Now, understanding what happens with GCs, it's important to know what the most common failure mode is. And talking to the service guys and my own experience as a service technician is that about 75% of measurement issues are caused by contamination in the analytical flow path. Now, I know everyone out there has clean, dry has clean, dry sample gas, but sometimes some other people have like other contaminants in there, like maybe compressor oil or amine or even solids and even just heavy hydrocarbons. What will happen over time in a GC is that you will see some contamination occurring over time, and so the restriction to flow will increase. And so as the restriction to flow increases because of the contamination inside the flow paths, we'll see some what we call retention time drift. And the peaks will come out a little bit slower and slower and slower every day. This can cause two major issues: incorrect peak detection and also incorrect component separation as well. So let's have a look at what I'm talking about here. When we're having a look at an analysis, we've got these two peaks here that we're measuring. And what we do inside the Emerson GCs is we have what we call inhibits. And so when we're not looking for peaks, we'll have the inhibit on. And when we want to look for peaks, we will turn the inhibits off, So we'll have an inhibit off, we'll detect the peaks. After we've expected to see the peaks, we'll turn the inhibits on again, and we'll do some kind of gain adjustment, getting ready for the next peaks, or maybe valve timing or something else we'll do while we're not detecting peaks, which is great. The problem is that these timed events are actually fixed throughout the analysis cycle. So what can happen is that when restriction builds up inside the GC, when we get contamination inside the flow path, what will happen is that the peaks will slowly drift. And they'll drift and they'll drift. They'll get later and later and later, but these timed events aren't changing. And so eventually what happens is that these peaks will drift and drift and drift until we start cutting off some of the measurement here. And here you can see bad peak detection at the end of this small peak here, because the peaks have shifted into that inhibit time, and when the inhibit is turned on, the GC stops looking for the peak, and so it's going to cut off some of that measurement. And so as a result, we're going to get bad measurement. We'll have bad response factors. When we look at this, on the response factors, what's going to happen is, because it's cutting off some of this peak, it's going to be cutting off some of the area. So the area in that formula, response factor equals area over cal concentration, that formula is now going to result in a smaller response factor because area is over cal concentration. The area is now small because we've cut some of it off. We're not measuring all of the area, so the area is going to be small, so the response factor will be small. And so this is how we detect that there's an issue in there with response factors. But understanding this is what happens over time, we can use this to validate that the GC is going to be working okay for the next period. Because what we can do is we can look at the chromatogram from today, and we can also look at the chromatogram from the last time we did a validation. So if we do a validation once a month, and we look at today's calibration chromatogram, and then we look at the chromatogram from a month ago, what you'll see is you'll see a little bit of a change in the retention time. Now, if that retention time change has happened over a month, it's a rule of thumb to say, well, okay, in the next month, I can expect it to move at least that much. And so if it's moved by 2 seconds over a month, which is actually quite a lot, but anyway, if it's moved by 2 seconds over a month, I can expect that it's going to move another 2 seconds in the next month. And in this case here, you can look at this chromatogram that's on the screen here, the blue chromatogram that's on the screen. That measurement is okay because I'm seeing all of that peak. But if that blue peak was to move by another 2 seconds, what would happen to the measurement at the end of that peak? We would start cutting off the measurement of that peak. So by understanding what the retention time drift was before and using that to predict what the retention time will be after a month or after 3 months, depending on your period of validation, you can predict if the GC is going to continue working correctly. And so by looking at the retention time from the last period to this period, you can predict what it will be from this period to the next period, and you can say, hey, look, if I don't touch this GC, if I don't make some adjustments here, it will start causing problems. So now is the time for me to fix it. So you're getting kind of an early warning to fix something before it actually affects your measurement. Now, once again, with the 370XA, we really tried to make it easy for you and build a lot of this understanding and knowledge into the GC. And so what we've done with the 370XA is we've incorporated these retention time alarms to say that, hey, if the normal pentane retention time starts to move too much, then we'll bring up an alarm to give you an early warning that there's excessive retention time drift. And in the ethane is the same. If that ethane peak shifts too much, it'll start going off the end of the chromatogram and we'll stop measuring the end of that peak. And so as a result, what we'll see is the bad measurement with the ethane. So what we've done with the 370XA is we've put these alarms into the GC. Now, these alarms are not alarms to say, oh my God, I need to get out there tomorrow, I need to fix this as soon as possible. This is really a predictive maintenance alarm. You get this alarm, then it's like, okay, in the next month, I need to do something. I need to go and do some work on this module. I need to either replace the module with a new module or an overhauled module, or actually overhaul the module and replace the diaphragms in the GC. So now, what we've done with the 370 is we understand that this is an early indicator of measurement problems, and so we've built that in to the analyzer to make it easy for you to keep it up to speed and running accurately. So that's pretty much it for the validating of GCs, but an important thing to remember that now that we've done all of this work with validating the GC and making sure that it's running correctly, is that we really need to document it. We really need to make sure that we document the procedure that we've followed and keep all of the records of the test. So during the test, we've looked at the alarm log, the event log. We've looked at the calibration chromatograms. We've looked at the final calibration report. All of that information should be stored in a folder, and it should be saved locally. And also, if you do have a test procedure, you need to make sure that you can sign off on it so that it's you sign off and say, yes, I've done this procedure. Everything was checked out okay, and here's my signature. It's important that all of the information that you collect during the verification test should be stored off-site. So you typically, these days, you would actually email it to someone in a central location. But also, you want to make sure that everyone that's a part of the verification gets copies, and all of this information is stored locally as well. Because one of the checks that we've done is to look at what happened before and what happened today. So we really want to keep the records from today there so that the next time we run this, we've got the information from today to use as our before results as for comparison. So all of that information is important to keep both off-site and also locally. So, in summary, basically validating a GC is we're really trying to check the performance of the GC in the period prior to the validation by looking at the alarm, the event logs. We've verified that the GC calibration is correct, not by running the cal gas as an unknown, but by verifying that the calibration response factors are correct. So we're proving that it's analyzing according to the laws of physics. Then we've predicted the future performance of the GC by looking at the retention time drift. And because we're talking about verification and validation here, we record everything and store it locally and remotely so the information can be used in the next validation. So that's it for the main presentation. I'll take some questions now. I've got some additional questions, so let's have a look here. Okay, so let me read the question. When reading the specific gravity of an analysis, what is that actually telling me about the gas sample? Well, actually, the specific gravity is a calculated value. So we calculate the specific gravity according to AGA 8. I think it's AGA 8. It's either AGA 8 or ISO 697-6 or GPA 2145, I think, or 2172. So that's a calculated value. It's not really telling you anything about the density. Well, it's telling you what the theoretical density is of that gas. It is a calculated value, and so it's not like it's measured gravity like you would see with a densitometer or something like that. Has there ever been a problem with the analysis of specific gravity? There's only a problem with well, it's not an analysis, but there's been a problem with the calculation of specific gravity if the analysis is incorrect. So if the analysis is incorrect, we calculate the specific gravity from that analysis. If that analysis is incorrect, then we have a problem with the specific gravity. Here, can you store the calibration gas certificates in the GC somehow for ordering? That's an excellent question. We do store the calibration reports and other reports in the GC in its normal memory, which is for calibrations, it's often over a year worth of calibrations. However, you may want to store it in another format. And what we do have with the XA series is we can actually upload documents. So you can upload a Word document, you can upload a text document, you can actually upload a PDF if you want as well, and you can upload that into the memory of the GC so you have a permanent record there of the GC. So if you have an inspection certificate where you're also looking at the sample system, maybe the pressure and the temperature and contamination, the sample system. If you have a check sheet like that in Word format or in PDF, you can actually upload that to the GC as well and store it in the memory of the GC so you have a permanent record that that test has been done. You have that at the GC itself. So that's a pretty nice little feature. Inside there, you should also find the manual and drawings for the GC in particular. So it's basically just a little memory storage for any customer documents that you might want to upload to the GC. So yeah, that definitely is possible. Okay, a question about on the chromatogram, with the shifting of the chromatogram, would the valve on-off timing need adjusting? It really depends. Sometimes when the peaks have shifted, if it hasn't changed the response factors, there's no need to change the on-off timing. But if it's changed the response factors, that may indicate that you are cutting some component and you may want to adjust the valve timing. So it's just the peak shifting themselves does not indicate that there's a problem with the valve timing, but it can cause a problem. So looking at the response factors will tell you if there's a problem with the measurement, which may lead to needing to change the on-off valve timing. Now, if you've got one of our C6 Plus GCs, propane and ethane are affected by the dual column valve timing, the valve 3 timing, and normal pentane and C6 Plus are the two components that are affected by the backflush timing. But that's really a subject for another webcast, valve timing. And I will say I'll put in another plug for the 370XA. We have this awesome little auto valve timing program where if you do see the response factors change for those 4 components, you can run the auto valve timing and it will actually automatically adjust the valve timing for you, making it very easy. Are all these validation procedures mentioned here apply well for process gas chromatographs? Yes, definitely, without a doubt. I would say, though, that you need to be careful with different detectors like FIDs and FPDs because the relationships, obviously, they're not thermal conductivity detectors, so they don't respond according to thermal conductivity. But as far as the relative response factors go, the theory still applies, is that, if they're all going through the same detector, and so if there's a relative change in the response, then there's something going on with the analysis. So I haven't really studied the FID or FPD response factors as far as relative response factors go. That's actually a program that I'm looking at doing in the future. But definitely with a thermal conductivity detector, that is valid. I will say, though, that the relative response factors won't be the same because the amount of quantity of the component, if you've got lots and lots of propane, if you've got like 70 or 80% of propane, then that will change the relative response factor compared to methane just because the detector is not truly linear, and so you need to consider that. I'm looking at some of these other questions. There's some questions here that I think I'll respond to offline. I always will get this, and I won't mention who's asked this question. But I said that running your cal gas as an unknown will not show issues. If I have a certificate that says 2% nitrogen and the unknown is coming up at 5%, would this not indicate an issue? Yeah, it indicates an issue. There definitely is an issue. And I'm not saying that if you run the cal gas as an unknown and it's wrong, there is definitely an issue. There's a big issue. Because if you've calibrated that morning on that cal gas and in the last 4 hours the analysis has changed by that much that is now analyzing that gas wrong, then there's a huge issue. There's a big issue there. And you mentioned nitrogen there, and nitrogen tells me straight away when I see there's an issue with the measurement of nitrogen, it tells me that there's an issue with a leak. You've got air getting in there. But the problem with running cal gas as an unknown is that it may give you the right results, but it doesn't tell you if there's a problem. The big issue with running the cal gas as an unknown is it hides an issue. It can hide an issue because, if you're cutting off your ethane because the valve timing is incorrect or something like that, then you calibrate it, you force it to read 5% ethane for that particular analysis, but it's cutting off some of the component. You don't know that because you've forced it to read 5% even though we know the analysis is wrong. And so when you go and measure a different gas, because you're going to cut off a different amount of that ethane in that peak, then you'll get an inaccurate analysis. So to qualify that, if you run the cal gas of an unknown, and it measures incorrectly, yeah, you have a problem. But if you run cal gas as an unknown and it gives you the same results as what's on the certificate, it doesn't mean that GC is running accurately. It may mean that your GC is hiding a problem. Your calibration is hiding a problem. Okay, there are some other questions that I will answer offline. There's some more detailed questions. And there's a question here about a pilot plant. If that person can send me your email in the question and answer, I will respond to that one in an email later on because that's a much more detailed question. But we're now at 1 hour and 8 minutes, so I'm 8 minutes over. My product manager over here is staring at me saying that I'm over time, so unless there's any more questions, I'll leave it another 30 seconds for questions. While we're waiting for questions, I would like to pitch that we have some more webcasts coming up. We have 4 more webcasts presented for the rest of the year. The next one is communicating with your GC through Modbus. So we're looking at RS-232, 485, and Ethernet. We get a lot of questions about Modbus communication, so that's going to be an interesting webinar. Installation considerations for GCs, where you should install them, what you should consider for installing them. The next one on August 11th is maintaining your GC at optimum performance levels. So that's really going into maintenance considerations for a GC. And sample handling system considerations for your GC, looking at what you really need to consider with your sample handling system as far as heat trace, filters, and stuff like that for your GC. So that's the series of webinars that we're going to have. This webinar will be available online. It will be available as the recorded version will be available into the future. And it will be, the other webcasts will also be available. And if you're listening to this on the recording, if you do have a question, you can also enter a question, and that will go to our email inbox, and we'll be able to answer your question over email. Just before I do finish it, I've got an excellent question here from Brody. Should you ever have to force cal when challenge a cal standard bottle? I sometimes run into this problem and the chromatogram looks fine. Yeah, sometimes you will need to do a force cal when you change a cal gas bottle, because the cal gas bottle that you have has an uncertainty in measurement. The new cal gas bottle has an uncertainty in measurement. The GC itself has an uncertainty of measurement, and so when you combine all three of the uncertainties, sometimes, especially the smaller components, they may, when you do a normal calibration, they may actually go outside of the response factor alarm. Doesn't happen very often, but it can happen. Also, if that cal gas that has been there for a while, if it's contaminated, maybe it got cold and some of the heavies have dropped out or something like that, then you can, you may have had a problem with that calibration with the old cal gas, and then you've got the new cal gas. Also, one other issue that can happen as well is that you can have a bad cal gas come from the supplier. You could get a new cal gas, and even though the certificate tells you what the composition is, that certificate can be wrong. A human puts a certificate on the bottle. Maybe they put the wrong certificate on. Maybe they entered the values incorrectly into the certificate. So you can't always trust the certificate, and so sometimes you will need to do a force cal when you're changing a cal gas bottle. However, whenever you do a force cal or whenever you do any calibration, you should be checking the response factors to make sure that they're in order of the thermal conductivity and they're in the ideal response factor range. And so if you do have to do a force cal, you should always check the response factors after to make sure that they are according to the thermal conductivities, according to the laws of physics. We're kind of getting a little off subject here, and I'm thinking now that maybe we should do a webinar on calibration and calibration standards. Can a calibration gas be brought back to original composition if the temperature of the bottle has been accidentally lowered below freezing? That can, if the bottle has been below the hydrocarbon dew point, and so the heavies have dropped out, but it has not been opened, so if it's been in storage and then you send it to site and you heat it up, you can heat it up, and you want to heat it up for a long time, usually overnight, well above, at least 30 degrees above the hydrocarbon dew point, then that cal gas will be okay. But if the cal gas has got cold, and the GC has run a calibration and some of the gas was taken out of the bottle while it was cold, that's a problem, and the cal gas is useless. it's no longer a good standard. So during storage, if the bottle gets cold, that's okay because you can heat it up overnight at least 30 degrees above the hydrocarbon dew point, and the composition will be back to where it should be. But if it is happened on site and there's a risk that gas has been pulled off of that bottle while it was cold, then that gas is ruined. Okay, question is there a list of relative response factors available? Actually, the relative response factors really depends on the individual unit. It depends on the model of GC, the kind of detectors, the branded detectors, and the flow path and the flow over there. So it's not like the relative response factors are the same for every single GC. We have the relative response factors loaded into our 370XA, but that's different to the relative response factors in our 700XA and is different to our Model 500. So we don't publish a relative response factor list. So that's a good question, though. Okay, I'm at 1 hour and 15 minutes, so I think what I'm going to do is bring this to a close. But before I do bring this to a close, I do have one final poll, if I can bring it up. There we go. Just tell us what you thought of this webcast. You know, awesome webcast, never attended one better. This was the best one ever, although obviously I've spelt best there incorrectly. Sorry about that. Or if you think it was a waste of time and you wish you could get that hour back, put that down there as well. So just tell us what you think about this. I'll have a look at the polls. And also, in the next poll question is just an open text box to give us your opinion. So once I see that people have stopped responding. Let's see. Oh, that's good. I've got some awesomes. That's good to see. So once I see people stop responding to this question, I'll bring up the next one, which is just an open comment on the presentation. Okay, so that's it for the webcast. Thank you for your time, everybody. I hope you did get some value out of this. It's a pretty important subject, especially those that are working in the custody transfer world. But everyone that's working with GCs, making sure that your GC is working correctly and validating the operation of GC is extremely important. And there's a lot of misperceptions out there about how to prove a GC is working accurately. So hopefully we've answered some of those questions and corrected some of those perceptions. And once again, I thank you very much for your time. Don't forget the other webcasts that are going to be held throughout the year, and also that this webcast will be available on our website at a later date, so that you can come back and refer to it at a later date. So once again, thank you very much for your time, and I hope you enjoyed it. Bye-bye.